compute the line integral of the vector field f equals 4x, 3y, so that's a vector field in the plane, components 4x and 3y, over the quarter circle part of x squared plus y squared equals 4, oriented counterclockwise, because orientation matters, in the first quadrant. Okay, so let's write down what we're going to compute here. So the line integral of the vector field, here's the generic notation, f dot dr is one generic notation over c. And then the working formula, we want the integral from a to b, f in terms of t, we've got to put that in terms of t, and then r prime of t, dr is r prime of t dt. So look at that computational formula on the right there and tell me what is it whispering to you? What is it telling you guys to do? You got to find r prime of t, but before you find r prime of t, what do you have to do? You got to find r of t. You got to find your parameterization, which is what we did mostly at the beginning of class, but there's a slight twist here. So how do we parameterize the quarter circle x squared plus y squared equals 4? R of t, we decided was going to equal what? What's x of t? 2 cosine of t. And y of t? 2 sine of t. We discovered that at the beginning of class. Now, how do you adjust the limits on t? Yeah, if you're looking at the quarter circle, t, it's not the full circle. T has to go from 0 to pi halves. That's important, right? Because that's how you get your limits of integration. Does that make sense? Okay, and then you guys told me I need to find r prime of t. So let's do that. R prime of t, what's that equal to? Negative 2 sine t, good start, and then 2 cosine t. Everybody okay with that? Now let's put f, you got to put f in terms of t at some point as well. F is given by components 4x and 3y. I think it'd be best to write it in terms of t. So in other words, in here, in terms of our parameterization, let's put in what x is. In terms of t, in other words, let's put in what y is. And let's write that right below the result. And then that makes taking the dot product really easy if you have these lined up. So f then in terms of t, so really it's f of x of t, comma, y of t. Maybe I should write that at least once so that you understand the notation. But we usually shorten it to, so it's f of x of t. There's 2 inputs, right? X of t and y of t. So x and y normally, but if we put it in terms of t, it becomes f of x of t, y of t. Okay, so from your parameterization then, you know that x of t is 2 cosine of t, right? That's x. Y of t is 2 sine of t, so what does f become? 8 cosine t and then 6 sine t, good. Now you've got everything lined up. Let's take the dot product. The dot product is our integrand, right? So we need that. That's what this formula is whispering to us. Okay. So let's take f, and I'm not going to write down the full notation, just f in terms of t, dotted with r prime, or r prime of t. And they're all lined up. So what do you get? Negative 16 sine t cosine t? Is it minus or plus? Plus. So plus 12? Sine, isn't it sine cosine again? Sine t cosine. Does everybody see what I'm looking at? Let's make sure. So I'm taking the dot product of these 2 vectors, right? So I'm taking this guy times this guy. There's my negative 16. Sine t, cosine t. Then I'm taking, of course, well, what happened? So now is the time for a break, and I'll come back with my alternate plan. I will not be defeated by a bad bulb. Where were we? Okay, so we just, we weren't quite done computing f dot r prime down here at the bottom, because what can we do with these 2 quantities? Oh, I think I was in the middle of showing you where it came from. So dot product, right? There's r prime, there's f. Can you see my, I don't know if you can see my cursor with this low light, but okay, there's R prime, there's F, and then F dot R prime, okay, we take this guy times this guy, there's your negative 16 sine t, cosine t. Then we take this guy times this guy, and there's your plus, you add it with dot product, right? Plus 12 sine t, cosine t, okay, and then, hey, these guys are like terms, aren't they? So what do we get? Negative 4 sine t, cosine t. So again, we let the formula tell us what to do. I mean, there are certain things you have to memorize. You have to memorize the formula. But then don't memorize a recipe of steps. Let the formula tell you the steps. So we've got our integrand, right? And we know our a and our b, the limits on t. So let's set this thing up and evaluate it. This integral then becomes what? You guys tell me. The integral from 0 to pi halves. Ooh, what can I do with that 4? Kick it out. Yeah, I like that. And then sine t, cosine of t, we just found out is our integrand. And then dt. Everybody good there? And then you could use a trig identity here, but that's the hard way to do it, right? Just u substitution is easiest. Because if you think of this guy as your du, kind of going backwards, sine of t is u, right? So what do you get when you integrate that? What's your antiderivative? So negative 4, 1/2 sine squared t. Because you think of sine of t as u, right? U squared over 2 or 1/2 u squared. And then you evaluate this part from 0 to pi halves, and that's times right there. So what do we get when the dust settles? Pi over 2. I think I said pi over 2, but I wrote pi. Magic, right? So what do you get? It's just going to be negative 2, right? Because the sine of pi over 2 is 1, sine of 0 is 0. There you go. It's the, well, if you consider F a force field, it would be the work done. It'd be a negative amount of work. So it's working against the motion by the force field in moving a particle along the curve from the beginning point to the end point. Beginning point given by r of 0, the end point given by r of pi over 2. Okay? Then the negative indicates, yeah, the vector field's working against the motion.